Good afternoon, class. Hello. For our chemistry class today, we'll be looking at a new topic altogether, which is chemical equilibrium. Alright? But before I ask you to tell me what you think about equilibrium, because I know that English word, equilibrium, right? So let me just take you through our specific learning objectives. These are the things we have to achieve, our learning objectives for this topic. Sections are what you need to know at the end of the class. So the first one there is, at the end of the class, we should be able to define what equilibrium constant is. We have Kc and Kp, and also define what partial pressure is. Then the third one, describe the effect of adding catalysts, changing the constitution of reactants and products, and changing the temperature or pressure on equilibrium constants. Okay, then also we'll look at Chatila's name before. Then also we're going to look at how we can apply the concept of equilibrium to the industry. Then specifically when the production of ammonia, because ammonia is a very important component of fertilizers, and you know that fertilizers help farmers to increase their crop yield. So we're going to apply the principles of equilibrium to the herbal process. How are the conditions of herbal process, how are they manipulated or changed so that we can achieve a higher ammonia yield? Then lastly, of course, because it's chemistry, simple calculation based on Kc. And the first thing we have to do here is to define what equilibrium is before we start looking at all this stuff. So back to you. When you hear the word equilibrium, what does that sound to you? What does it mean to you?
It's a constant, like it's not changing.
Thank you. I love that word, constant. Okay, so you'll be hearing that word frequently in this topic. Okay, my dear?
Maybe start position, like in physics, where the object starts from.
Okay, he says static position.
Like
or
where it
start.
starts from.
Okay, where it starts from. Okay. So if you are bringing physics idea, then you can talk about it being balanced. You know, in physics, we have these balanced forces and unbalanced forces. So we see that they are in equilibrium. That means they are on the same level. None of them is changing. So if that's what we imply. Thank you for that. Okay. So the first thing I would like to define here is chemical equilibrium. So in chemistry, when we say a system is under chemical equilibrium, what we mean is that, first of all, that system or that reaction is a reversible reaction, first of all. So we have the state of reversibility, that's a reversible reaction. Also, so that the system is, or the reaction is occurring under a closed system, all right? Under a closed system. So now, these two things are written on the board. I want you to put it, just put it somewhere in your cerebrum. The cerebrum is where you think. Then, because we still revisit it along the line because of our study. So, a chemical equilibrium refers to a dynamic state in which the forward reaction and the backward reaction in the chemical reaction are occurring at the same space. All right? So, like we're saying about balanced forces, when they are balanced, the rate at which the forward reaction is taking place is equal to the rate at which the backward reaction is taking place. So that's why I use this concept, reversible reaction. So can you tell me what a reversible reaction is about, if at least from your O-level chemistry? Anyone?
Reactants, it can go both ways.
Okay, thank you. The reactant, the product can also react back to form the reactant. So we have this sign that we use. So for example, I have A plus B. These are the reactants, right? And I have C plus D. So this system, this reaction is referred to as a reversible reaction. This sign is used to denote or signify a reaction that is reversible. So probably in your exam or anywhere, maybe your personal study, and you come across this sign, it means that the reaction is reversible. But of course, if the sign is, if you just have a single arrow pointing to your right hand side, you know it is not, it's an unreversible reaction. So you have this sign there that denotes a reversible reaction. Also, I said it occurs in a closed system. So if a chemical reaction is occurring in a closed system, it means that if eventually one of the products is a gas, it will not escape. It will remain in the reaction vessel. Alright? What we mean by closed system. Also, an open system, maybe you're just reacting maybe in an open beaker. So if you have a product that is gaseous, of course the product will escape. But in the closed system, all reactants and products remain, even if they are gases, they will remain in the system because there's no way for them to escape. Okay? Chemical equilibrium is a dynamic state in which of a chemical reaction in which the forward reaction is occurring at the same rate with the backward reaction. Okay? So I would like to see you write it down on your notes. Okay, so we have a graph here. Let's illustrate a chemical reaction that is under dynamic equilibrium using a graph here. Now, at the beginning of your reaction, you have your concentration against time. So because you have your reactant, the rate of your reaction will increase at a very fast rate at the beginning of your reaction because you have your reactant and you have both of reactants reacting together. But a time will come in which the rate of reaction will kind of will decline or kind of reduce. Why? Because a point will come in which more molecules or more particles of the reactant have already reacted to form the product. So the rate at which the product will be formed will no longer be as fast as it was initially. Okay? Then, what now happens when all the reactant particles have reacted to form the product? If that system is under equilibrium, the product form will react to form back the product, to form back the reactants. So that's where the concept of this graph comes in. You can see here, and it's an equilibrium reaction. Not all the reactants end up as product. There is not without 100% conversion because some of the product also do what? Break down or they react together to form the reactants. So here we have the rate of reaction is fastest at the start of the reaction, like I explained, because you have more molecules or particles of the reactants reacting together. So the rate of the reaction is fastest at the beginning of the reaction, but gradually the forward reaction slows down because the reactants are being used. Okay? Then, afterwards, you will see that the product also will react to form back the reactant. Okay. Okay? Now, we'll go on to the Chancellor's principle. I don't know if have you heard this word before? The Chancellor's principle. Let's go on to the Chancellor's principle. Now, this one, the scientist came up with this principle that when a change is applied to a system in dynamic equilibrium, the system reacts in a way to oppose the effect of that change. We've already learned about the concept of dynamic equilibrium. We've talked about what it means. Now, Le Chancellor came up with a principle that when a change is applied to a system under dynamic equilibrium, the system will react in a way to oppose the effect of the change. So let me give an example. There was I think 2 years ago, people, I had a very long day. People are telling me, trim your hair, trim your hair, trim your hair. I said, no, I'm not trimming my hair. So one day, I went to make my hair. The hairdresser was like, she said, the tip of my hair is not healthy. It's too weak. That I should trim it. So like, if I trim this hair, my hair will not be long again, it will be short. And I had a very long hair. As long as this place. So she said I should trim it. So I said, no problem, trim it. You know, I should trim that hair. The day that hair grew, I was very surprised. She trimmed and it became short. She said that my usual long hair. You see the rate at which the hair grew back longer, I was very surprised, and that's the concept of this legitimate principle. For example, you have a rose bush growing with intense, but if you pull it, it will grow back with vigor. And that was happened to my hair. When I trimmed that hair, within 2 months, I saw a massive difference. The hair grew back faster than I was grooming the hair from little. The hair grew back. Why? Because the hair has been cut. So let me make my hair a chemical system in equilibrium. So as I've cut the hair, it has to react in a way to oppose the change, so that you can attain back the length of that hair. People always say that if you trim your hair will grow back faster. I never believed it until I trimmed my hair. That should be like 21 years ago. That was when I believed that concept. They only say trim your hair. So now I believe that concept, and I'm also applying it to this topic today. So if you have a rose bush that is growing, if you prune it, it will go back with intense or increased vigor, so that you can attain back the level it was before. Also, then in chemistry, if you have a system in a state of equilibrium, if you change something in that system, the system will move or react in a way to oppose that change. So I'll give you an example here. For example, you have still using this same chemical reaction. So we are assuming that this reaction now is occurring in a closed system and it is under dynamic equilibrium. After anything, any factor, any condition in this chemical reaction, according to Lechatelet's principle, this system or the chemical reaction itself will react in a way to oppose the change. Now, what are the factors that ordinarily affect a chemical reaction? Temperature, okay. Yes, atoms, yes. Concentration of the reactant, okay. And also pressure, right? If we are dealing with, we talked about temperature, we said pressure, and we also mentioned concentration of reactants. Also catalysts. If I change any of these conditions in this chemical reaction, this system will move in a way to oppose the change. So let's move forward. So that will bring us to the concept of equilibrium constant. I believe you saw it in the syllabus. Equilibrium constants, Kp and Kc. But first of all, we'll deal with Kc first, then later we'll also look at Kp. So now this equilibrium constant is not affected by a change in concentration. To maintain the constant, the position of the equilibrium mixture changes. This equilibrium constant now is not if you change the concentration of the reactant or the product. It's not affected by that. Because I will still give you the expression for that. And that will show you why it is not affected by a change in concentration. So if you increase the concentration of a substance, the value of the Kc will theoretically be affected, as it must remain constant at a particular pressure. The concentration of the other species change also to keep the Kc constant. So this will lead us to writing an expression for the Kc. I'll still bring back my reversible reaction. So for this now, we are expressing this in relation to concentration. So the product, the concentration of the product, multiply it by the concentration of the reactant. So if we had some numbers here, this A will carry raised power 2. But we don't have, just have one each. So that's what we have here. So this one is not part of it. So this is the equilibrium constant in respect to concentration of this chemical, this reversible reaction. So in this case now, we can say that if you change the concentration of C according to the Challenger principle, this system will react in a way to ensure that it brings down the concentration of C back to the normal level. So that is why Kc will not be affected, because if you change C, the system will also react in a way maybe to produce more of these reactants. So overall, the equilibrium constant is not affected. So let's go to the next slide. So now the next thing we have to look at here is factors affecting the position of equilibrium. Just like stated here, describe the effect of adding catalysts changing the concentration of the reactant or product, or changing the temperature on the equilibrium constant. So factors affecting the position of the equilibrium. Now, equilibrium position can either shift to the right or to the left. You can shift towards the product or shift towards the reactant. So let's look at the factors that affect the position of the equilibrium as you have it in your syllabus there. So we're going to use this esterification reaction to explain this concept. So you have ethanol reacting with ethanoic acid to form an ester, and water as a product. So this is your equilibrium constant, which from what I gave you previously, the product of the concentration of the product divided by the product of the concentration of the reactant from the previous slide I gave you. Okay? So if we increase the concentration of this ethanoic acid, what do you think the system will do to ensure that the system or the chemical reaction remains at equilibrium? If I increase this concentration, if I increase concentration of the ethanoic acid, so this system now will react in a way to ensure that it brings down this concentration back to the normal level. So what will happen is the equilibrium position will shift to favor the production of the product. So the equilibrium position will shift to the right hand side, favoring the production of more product, meaning that this reactant will be used up. Because if you facilitate more product being formed, it means that you are using up the reactants. So in this case now, we have increased the concentration of one of the reactants. So the system will react in a way to ensure that the amount of these reactants come back to the normal equilibrium level. So how can it achieve that? It can only achieve by facilitating the production of more of the products. So the equilibrium will shift to the right hand side to restore it back to equilibrium. Okay, so what if we reduce the concentration of this ester here? How will this chemical equation, how will it react? What will be the response? If we reduce what's an ester here? Okay, let's see it and know it. If we reduce the amount of the ester, are you sure it will increase the amount of the product of the reactant? Think about it again. If I reduce, I didn't say increase, if I reduce the amount of this ester, which is the product, so how will this system react to bring back the system back to equilibrium? Sorry? Okay, yes, data will reduce. Okay, so what does that lead to? If the reactant is being reduced, what is happening? That means the reactant are reacting to do what? Follow that line of thought. Thank you. So if I reduce the amount of this ester now, the system will act in a way to ensure that the original or the normal amount of this ester is restored. So what it do is that it will facilitate more of this reactant to start reacting to produce the product. So the equilibrium will shift to the left. So it will shift to the right. Favoring the production of more of the ester because you have reduced its concentration. So the system will react in a way to ensure that the concentration is restored back to normal level. Probably it was 5 mole per dm, and you reduce it to 2 moles per dm. So the system will ensure that the amount goes back to 5 mole by ensuring that this and this react more. So the system, the equilibrium position will shift to the right, go to the right. That's what we have to. If you reduce the amount of one of the reactants, how will this system react? Or what will be the effect? Which is how your question will come in your exam. What is the effect on the position of the equilibrium if the concentration of the reactants, in this case, ethanoic acid, is reduced? So how will this system react to nullify that change or to restore it back to equilibrium? If the concentration of this ethanoic acid is reduced, the system will shift to the right, favoring the production of more of the reactants so that it can restore it back to the equilibrium level. Does that make sense? So this is summary of the whole thing. You can put this down. Changing the concentration, the effect on the equilibrium position. If we increase a reactant concentration, like I said, equilibrium will shift to the right. If you decrease the concentration of the reactant, equilibrium will shift to the left. Also, if you increase the concentration of the product, equilibrium will shift to the left, then vice versa for this one. So this is just like an hack or trick for you on this aspect. Effect of concentration on equilibrium position. More products will lead to more reactant being formed, so the equilibrium will shift to the left. So this is just a summary of it, which will help you in your examination. But this is just like 1/10 of what you need to know. Can I move on to the next aspect? Okay. Because I want to believe that you understand this concentration, the effects. Is it clear? Please feel free. If it's not clear, I will say yes. That's why I'm here. That's why I'm here. Here we go. Is it clear? Please be free to ask some questions. Okay, so we can go on. So for example, let's look at this process here. Sulfur dioxide reacting with oxygen to form SO3. Predict the effect of decreasing concentration of the product on the equilibrium position. So who answered that for us? If you decrease the concentration of SO3, sulfur trioxide, what will be the effect on equilibrium position? This is the product, right? Okay. Fine, are you sure you need to be next? Use this. You need to be very clean. Move to be. Okay, this one, this. We're looking at this one with this. Then we'll go to this. I know I picked this first. This is the question I'm talking about. We'll still go back to this second one, to the first one. I picked the second one first. So do you agree with the answer? So if you decrease the concentration of SO3, the equilibrium will shift to the right, so that more product will be formed to restore equilibrium. Okay, what about this? We need the effect of increasing the concentration of oxygen on the equilibrium position. Still go to the right. Because now you have more reactants. So the system reacts in a way to ensure that equilibrium is attained. Thank you for that. Okay, so that's the answer there.